Hey everyone, and welcome to The Explainer. Today, we're literally putting on our lab coats. Imagine you're a machine learning doctor, and your patient, well, it's an underperforming predictive model, and it is sick. It's making bad predictions, and honestly, the stakes are super high here. When a model gets sick in the real world, it's not just some quirky math problem. We're talking about costing a business serious money, completely failing to detect fraud, or even worse, making bad medical predictions. So your job? You've got to figure out exactly why it's failing and how to cure it. So today, we're going to master the absolute most useful diagnostic skill in all of machine learning, the bias-variance trade-off. Okay, so let's dive right into this. It's a totally universal and frankly incredibly frustrating problem. You just spent days, maybe even weeks training a model, and in your dev environment, it looks absolutely fantastic. But the exact second you test it on new, unseen data out in the real world, it just completely falls apart. It has massive test error. Imagine you train this housing price predictor. It absolutely nailed the historical data, but when you launch it live, it's out there confidently predicting negative prices for luxury mansions. Like what? Where exactly does that error come from? Why didn't it learn the true pattern? Well, answering that fundamental question is your key to unlocking much better, more reliable performance. Here's our diagnostic playbook for today. We'll hit the source of error and bias versus variance, the modern twist known as double descent, how to diagnose your model, the cures like regularization and ensembles, and finally, the complete diagnostic workflow. Let's get to it. Kicking things off with part 1, the source of model error and bias versus variance. So let's look at the underlying biology of our models. Basically, every single prediction error your model makes stems from just 3 sources. That's bias, variance, or irreducible noise. Now, irreducible noise, that's just the randomness of the universe. Maybe a sensor misfired or someone just fat-fingered the wrong digit. No model can fix that, right? But bias and variance, those are the 2 vital signs you can actually treat. Let's define the first one. Bias is your model's systematic error. Imagine training the exact same model on a bunch of different batches of data and then averaging its predictions out. Bias is the gap between that average and the absolute truth. If we're using medical terms, think of high bias as chronic stiffness. The model is just way too rigid. It's too stubborn to listen to the actual symptoms and capture the real pattern. It's literally like trying to fit a perfectly straight line to a U-shaped parabola. It's going to consistently miss the curve no matter what you do. In the biz, we call this underfitting. On the flip side of the diagnosis, we have variance. And variance measures your model's sensitivity. It basically asks, how wildly do your predictions swing if you just slightly change the training data? High variance means your model is essentially hypersensitive. It's paranoid. Instead of learning the real underlying signal, it just starts memorizing the background noise. It's exactly like that student who memorizes the precise phrasing of a practice test, but then completely panics and fails the actual exam because the math questions were tweaked just a tiny bit. Imagine a wildly oscillating degree 20 polynomial that sharply zigzags all over the place just to touch every single data point perfectly. That hypersensitivity, that's high variance. Or, as we normally call it, overfitting. So the absolutely crucial point here is this classic trade-off. For a fixed amount of data, you cannot minimize both of them at the same time. They're sitting on a seesaw. But why does this seesaw even exist in the first place? Well, it all comes down to flexibility. If you push your bias down by giving the model the flexibility to bend and capture that true complex pattern, you're inherently giving it the flexibility to bend to the random noise too. So the variance goes up. Conversely, if you push variance down by making the model simpler and way more rigid so it ignores the noise, well, now it loses the ability to capture the true signal, and boom, your bias goes up. And this brilliantly illustrates that classic U-shaped error curve that every ML practitioner eventually sees in their sleep. Let's walk through it. If your model complexity is too low, you're hanging out on the left side of the curve. You've got high bias and high total error. Your model is chronically stiff. But push the complexity too high, moving over to the right side, and now you have high variance and high total error. Your model is way too sensitive. As a machine learning practitioner, your entire job, literally the reason you spend hours hunting and tuning hyperparameters, is to find that magical, just right middle row. That's the very bottom of the U-shape. It's the sweet spot where both bias and variance are moderate, giving you the absolute lowest total error possible. Moving on to part 2, the modern twist, known as double descent. Okay, now that we understand the classical rules, I need to introduce a massive plot twist that completely shook the machine learning world back in 2019. Classical theory tells us that once you pass that sweet spot at the bottom of the U-curve and make your model too complex, your test error is just going to keep getting worse and worse. But modern research shows that if you keep pushing model capacity far past the point where it perfectly memorizes the training data, which is a critical point we call the interpolation threshold, an amazing phenomenon called double descent kicks in. The test error can actually start to decrease again. No way, right? Imagine forcing a curve to touch 1,000,000 data points perfectly. It becomes this jagged, useless, highly variable mess. That's the peak of the threshold. But push even further, and you enter a second descent. This is exactly why massively overparameterized models like GBT or large ResNets can exist entirely in this wild new realm and still generalize incredibly well. Let's break down these three modern regimes. First, when you have far fewer parameters than samples, the classical trade-off applies perfectly. But look at that middle row, the interpolation threshold. This is where your model has just enough parameters to perfectly fit the training data. It's basically forced into a very specific, twisted, jagged solution just to thread through every single point. Because of that, variance absolutely peaks and test error wildly spikes. But if you move to the third regime, where it's massively overparameterized, the model suddenly has millions of possible ways to fit the data perfectly. And here is the truly fascinating part. The learning algorithm itself tends to implicitly pick the smoothest, simplest path out of those millions of options. That implicit regularization kicks in, and the test error drops. So, the golden rule of the modern ML era? Never, ever stop right at the interpolation threshold. You either need to stay well below it, or push well past it. All right, part 3, diagnosing your model. Let's step back into the clinic for a second. How do we actually read the symptoms of our specific model to know if it's suffering from bias or variance? Well, your patient's vital signs are the training and test errors. If both your training error and your test error are running a high fever, meaning they're both consistently high, your model is underfitting. That's a clear-cut bias diagnosis. It's just too stiff. Now, if your training error is beautifully low, but your test error is sky-high, your model is memorizing the data but totally failing to generalize. That's a variance diagnosis. It's hypersensitive. And hey, if you're watching your model train in real time and you see training error dropping while test error starts rising, you are actively catching the model overfitting right before your very eyes. Let's see how these errors actually build into learning curves, which are arguably the single most practical diagnostic tool you have in your toolkit. Instead of just taking a single snapshot of vitals, a learning curve shows your model's trajectory as you feed it more and more data. If the curves for your training and validation errors are flat, high, and pretty close together, you've got high bias. And crucially, this tells you that gathering more data is completely useless. I mean it. If the model's brain is already completely full, pouring more data into it isn't going to change a thing. It simply lacks the capacity to learn anything new. But, on the other hand, if there's a massive gap between those curves, and you see that gap actively shrinking as the data size grows, you have high variance. In that specific case, yes, spending weeks collecting more data acts like a calming supplement, and it will actually cure the hypersensitivity. Section 4, the cures, regularization and ensembles. Okay, we've read the symptoms and we've made our diagnosis. Now it's time to prescribe the heavy-duty treatments to actually fix the model. If you diagnosed your model with high bias, remember, it's suffering from chronic stiffness. We need to prescribe flexibility. We've got to untie the model's hands. To cure it, you can engineer more complex features, like throwing in some polynomial or interaction terms, just to give it a richer vocabulary. You could also completely swap out your simple model for a much more flexible one. Think moving from a super rigid linear regression to a dynamic tree ensemble. You can also try turning down your regularization strength. Think of regularization as a tight constraint. Turning it down gives the model a lot more freedom to learn those deeper patterns. Or, honestly, sometimes it might just need to train a little longer. But what if your model has high variance? It's highly paranoid, it's hypersensitive, and it desperately needs to be calmed down. Honestly, the absolute best cure here is just getting more training data. But if you can't get that, you can apply ensemble techniques like bagging. Random forests are a really great example of this. You should also prescribe some physical therapy by increasing your regularization. Go ahead and crank up the L1 or L2 penalties or boost the dropout rate in your neural networks to force the network to be more robust. Finally, perform some feature selection. Stripping away noisy, irrelevant features is basically like removing distractions from a panicked student's desk. It lets them actually focus on the real core lesson without getting totally overwhelmed. Now, when you're prescribing ensembles to treat your model, you really have to choose between the two undisputed kings of the space, bagging and boosting. Bagging trains multiple independent models and averages out their predictions. It's kind of like getting a second opinion from 10 different doctors to naturally cancel out any single doctor's individual crazy ideas. This directly attacks and reduces variance. Boosting, on the exact other hand, builds models sequentially. Each new model is specifically trying to fix the errors of the previous one. It's like one highly focused doctor repeatedly correcting their own specific mistakes over and over again. This directly attacks and reduces bias. So, your golden rule here is pretty simple. If your base model is wildly complex and hypersensitive, use bagging. If your base model is too simple and chronically stiff, use boosting.
Bringing it home with Part 5, the complete diagnostic workflow. Let's bring all this theory and all these medical treatments together into one cohesive, step-by-step action plan that you can actually use on your very next project. Blindly applying random fixes without a proper diagnosis is literally the #1 reason data scientists waste days of compute time. If you follow this workflow, I promise you will save yourself hours of random guessing. Step 1, train your model and immediately check your train and test errors to diagnose whether it's bias or variance. Step 2, if variance is your enemy, don't just guess. Generate a learning curve to prove mathematically whether getting more data is actually worth your precious time. Step 3, generate a validation curve by sweeping a complexity parameter like tree depth to visually find that U-shaped sweet spot. And step 4, fine-tune your L1 or L2 regularization. Regularization acts like a continuous dial, letting you slide smoothly along the bias-variance curve until your error drops to its absolute minimum. This entire clinical process, it really only takes about 10 to 15 minutes of compute time, and it completely replaces weeks of trial and error. To wrap things up today, I want to leave you with a thought-provoking question based on what we've covered. Imagine a totally perfect world. If you could completely remove all irreducible noise from your dataset, how would that shift your optimal model complexity? Would you be able to push your model's variance higher without any penalty? Seriously, think about how that classic U-curve would change if there was absolutely zero background noise for the model to accidentally memorize. I highly encourage you to go test this out in your own code and see what happens. Thanks for joining me on this explainer, and happy diagnosing.